So in this video, we're just going to introduce the second fundamental theorem of calculus. So the claim is that, this is the second fundamental theorem of calculus. The claim is that if we have a function little f of t that is continuous on a closed interval that contains a, and big F of t is any antiderivative of little f on that interval, then the derivative of the definite integral evaluated on the closed interval from a to x, and in the previous video we saw that this integral here, not the derivative of it, but this integral gives us the signed area under the curve as a function of x. So the claim is that if we want to take the derivative with respect to x of the function that gives us the signed area under the curve of f on the closed interval from a to x, that we can just replace this derivative with f of x. In other words, we'll take the upper bound of integration and drop it in for the variable t, and this will be the derivative. And a couple things here just to comment on. It should be clear that if we take this antiderivative, we do get a function of x, because when we integrate, what would we get here? We would get, when we integrated this, if big F of t is an antiderivative, you get the integral from 0 to x of f of t dt equals the antiderivative at t evaluated from the lower bound of integration to the upper bound. And the fundamental theorem of calculus says to us, just put in the upper bound of integration and subtract from that the antiderivative evaluated at the lower bound of integration. So it's clear that this right here is a function of x. F of a is just a real number, so f of a is just a number, and we have a function of x minus a number. So if we're taking the derivative, you would need to take the derivative with respect to x, and you would be taking the derivative with respect to x of big F of x minus big F of a. So when you use the second fundamental theorem of calculus, so I'm going to skip the proofs. I'm not going to focus on proofs in this video. So just applying the second fundamental theorem of calculus, let's say we wanted to take this derivative. If we did it without the second fundamental theorem of calculus, so if I said, hey, I want to take d dx of the integral from a to x of 2t squared plus t minus 4 dt, and I wanted to do it without using the second fundamental theorem of calculus, you would first need to integrate. So we would get d dx of, and then we would integrate this. So this would be 2/3 t cubed plus a half of a t squared minus 4 times t, and we would evaluate this from a to x. And then you would use the fundamental theorem of calculus to recognize that this means you plug in the upper bound of integration, so you wind up getting 2/3 x cubed plus 1/2 x squared minus 4 times x minus parentheses, and then the second fundamental theorem of calculus, the first fundamental theorem of calculus says plug in a, your lower bound of integration, so we get 2/3 a cubed plus 1/2 a squared minus 4 times a. And then once we integrated, we would then differentiate the result. So we would wind up getting 2/3 times, and then we would differentiate x cubed, which would be 3 times x squared plus 1/2, and then differentiate the x squared, so we'll get 2x, differentiate the minus 4x, which is just minus 4, minus, and this right here is just a number, so when we take the derivative of a constant, this is a constant because a is just a real number, you get 0, and then you simplify, 2x squared plus x minus 4. And so that would be differentiating the definite integral without using the second fundamental theorem of calculus. The second fundamental theorem of calculus says, hey, if you want to take d dx of the definite integral that gives you the signed area under the curve as a function of x, The second fundamental theorem of calculus simply says that you can take and Well, look at your function little f of t that's inside of here, and everywhere you see the t, replace the t with the x. So I would get 2x squared plus, replace this t with x minus 4. And I get the same thing that I did here by integrating first and then differentiating. So the second fundamental theorem of calculus gives us a nice shortcut for finding this derivative. And again, if you want to back up and pause on either this slide, which gives a formal proof, or this slide, which gives a more informal proof, you can look through and see the proofs for the second fundamental theorem of calculus. So one more quick example. So find the derivative of the definite integral of the cosine of t times the square root of t divided by the square root of t squared minus t minus 2 dt. And it says to do it with and without using the second fundamental theorem of calculus. But in this case, the idea behind this example is really simple. The idea is that integration is really difficult, and most antiderivatives don't have elementary functions for the result. In other words, it's not easy to calculate an antiderivative. So this is one where if we tried to calculate this antiderivative, we would most likely get stuck and not be able to do it. So integrating first, which is what you would need to do if you were going to differentiate without using the second fundamental theorem of calculus, integrating first would be hard. But fortunately, the second fundamental theorem of calculus says, hey, if you need to know the derivative with respect to x of this definite integral, everywhere you see a t, just drop in and replace that t with an x. So I don't need to have to be able to integrate first before I differentiate. So there's the derivative of this kind of ugly, nasty definite integral.